So, welcome everyone. Good morning from Germany, and good day or good evening wherever you are. And welcome to this keynote. Thank you for the invitation, Sabine. And yeah, as Zach already mentioned, the battery space is incredibly dynamic. And if you just follow the news, you will probably find at least one or two claims of the next huge battery breakthrough that will change everything and that will make cars go 1,000 miles on a single charge and recharge in 2 minutes. And then mostly you never hear of these news stories again after that. And so I try to, actually, it's a pretty good introduction. We didn't plan that, Zach. So my talk will be on battery trends from research to reality. So it's not just about making a breakthrough discovery that works in the lab, but it's also about bringing that innovation to reality to actually support the goals that we want to achieve. And so these goals, I guess whoever is watching is very aware of this, but one of the main reasons we are actually looking into battery storage and into storage in general is that in order to decarbonize our energy systems using solar and wind, which are not available 24/7, we need new flexibilities. And these flexibilities, if we think about the electricity space, there's basically two different kinds of it. One is the old way to do it. It's power grids. And power grids are a spatial flexibility, which means if you have power generation at one point and you don't need the power there, you can take the power to a different place at the same time. This has been working for over 100 years very well, and it's a standard way to deal with flexibility in our current energy system. The other way, and this is new, is electricity storage. And obviously, electricity storage, what it does, it's a temporal flexibility, so it decouples the time of generation and usage on the same site. And if you look at the whole energy system, it's not just electricity, and we are getting into a system that is more and more intertwined. So very briefly, you can see electricity on the top, then you can see heating on the right-hand side, and there is a connection through heat pumps, for example. Then you have the gas grid on the bottom of the slide. Also, we have connections there. You can make renewable hydrogen, other gases from that, and then basically turn them into electricity again. So the arrow has two sides. And then on the left-hand side, we have transportation, which currently is mostly done using fossil fuels, but which is changing rapidly. And now we are talking about batteries. So where do batteries play a role here? Basically in two spaces. Batteries are very, very versatile because of their modularity. And so we find them in many, many places. We find them in electric cars, we find them in home storage systems, we find them in huge energy installations. And if we look at this chart and see where we can find them, it's in the transport and electricity space. And with the idea of doing a keynote on battery storage systems from research to reality, I wanted to focus on two concrete examples, how recent research can support this energy transition that we see here. And there has been a lot of talk about the interaction between the mobility and energy market. And so I thought, hey, why not take an example from that space? And so if you think about electric cars, they are basically batteries on wheels. Don't tell the car people this, but for a battery scientist, an electric car is a battery with wheels. And there are two ways how vehicles interact with the energy system. The one is a bidirectional charging. So whenever you charge the car, it becomes a grid asset. And if you have a bidirectional power flow, it becomes basically a power plant, a very small power plant also. And the other thing is second life, which gets a lot of media attention every now and then. And the idea is basically to repurpose car batteries that are not good enough to stay in the car, but still have a decent shelf life maybe to be used in a less demanding application, such as large-scale battery storage. And actually, the picture you see on the right-hand side is a Second Life battery storage system made up of old car batteries. Okay, and if we are planning something very new in the realm of, well, we have to switch our whole mobility to more sustainable ways. That includes electric vehicles. We need to switch our electricity system. And then we want to intertwine these two sectors that are rapidly developing on the way. There's a lot of challenges we're facing. So there is the question of technical standards. There's the question of transaction costs. How much money does it cost me to put a battery from a car into another application? Like, who is doing the job? Does he need a special education? What is the transportation of the battery cost? And so on and so on. And a huge challenge, obviously, is market design. In many countries around the world, energy storage systems don't quite fit into the traditional ways of the energy laws. And so we need to very actively develop these legislation in order to support the flexibilities that we need. And that's all very, very important and very exciting also. But for today, I want to focus on a challenge that is very much battery related and also research related, the question of battery aging. Because if we want to make batteries a key component of our mobility and of our energy sector, we need to make sure that the batteries are working as intended. And also, we want to do an energy transition in order to have a more sustainable way of living. And so a battery that ages too quickly can quickly become a liability in terms of resource consumption and such. So battery aging is an incredibly important topic, and I'd like to tell you a little about the current developments in the research space and how we can bring them to reality. But to start, I want to go back to zero and think about, well, what's aging actually? I mean, we all know a little bit about it, but so I thought I'd come up with a very clear example. So what's aging in terms of humans? And if you look at the actor Hugh Laurie, you know him probably from Dr. House. There's two things that you can observe over the 25 years between these pictures. Two things happen. On the one hand, he gets more beard. And on the other hand, he gets also, I would say, a better way of dressing. So he gets fancier clothes. So that's the two things we can observe from these pictures. But what about batteries? So when batteries age, a lot of things happen. And you really shouldn't ask a battery scientist, hey, what's happening when aging? Because he will give you his whole dissertation and many more. But if we look at it from an angle of, okay, from the application side, what's the most important things from the application side that happens? There's two things that we can see. On the one hand, the capacity of the battery goes down. So that means your car will not drive as long on a single charge, or your phone will not be available for as long as it used to. And the other hand is you have an increase of internal resistance, which means that the power capability of the battery will go down, or it will heat up more when used, which might become a problem for your system design. And these results are derived from lots and lots of lab tests that are done around the world. We have a very big testing facility in Aachen, but there's many research groups and companies around the world that operate these huge labs in order to understand battery aging better. Another thing absolutely is that when aged beyond a certain point, batteries might become safety critical. So it's not just an economic question of losing performance, but it might also become a safety critical act. So we should look at it very, very closely. So I promised to talk about concrete example because I think it's the best way to get a good understanding or a first overview about the problem. And so we have two applications where battery aging is very, very critical. The one is vehicle to grid and the other is second life. And the key questions that you could ask yourself coming from these applications is, in the vehicle to grid space, if I use my battery for more than just driving, is this hurting the battery? And it probably will hurt the battery a little bit at least. But the question is, how much revenue can I make off of this additional usage? And is it economic, all things being equal? The other question, or another question when you think about second life is, well, first, maybe just if you want to sell a used car is, hey, how much is my used car still worth? So resale value is a huge topic. But if you think about second life, you would want to change the battery from the first application into the second one at the best point. But what is this best point? And how can we estimate that? And how can we make sure that our system is working as intended? So the optimal time for replacement is a huge question in that space. And now let's look into how can we achieve good results in this regard. And one example is vehicle to grid. I guess most of you know certain things about it. A vehicle to grid can have different complexities. The most simple vehicle to grid operation would be, I'm charging electricity at a certain point in time when, for example, electricity is cheap. So it's not a bidirectional power flow, but it's just a smart charging, if you will. We also call that V1G because the power has only one direction. And if you look at the stock index in Germany, and if you think that in a future energy system, the stock price might be visible on the end customer side, under current conditions, you can save about 3 cents per kilowatt hour if you smart charge your electric car. Other things is you might be able to trade energy. So buy at the lowest point in time, the lowest price, sell at the highest. So on good days, you could make about 15 cents per kilowatt hour on the spread. And then as it becomes more complex, you might be able to offer system services such as frequency reserve and so on. And both the complexity and the profitability of these systems increase as we go down. So this is great. We can make additional revenues with our car. Sounds great. But is there a catch? Well, there are some challenges, I would say. And the one thing is we have transaction costs in vehicle to grid. So if you want to offer system services, you need a meter that checks if you're actually doing what you're supposed to do. You need maybe additional hardware. So a bidirectional charger is more expensive than a traditional wall box. And you need communication. And so all these transaction costs can add up into the 3 to 30 cents per kilowatt hour. So we need to really, really make sure that these soft costs go down through standards and through good legislation. But then the question is, what about battery aging? Because if I use my battery in more ways, it might age, which has costs. So what we're looking for really is a cost function for battery aging. If I do this additional service, how much money will I lose in terms of aging? And how do we do that? Let's go back to research. The traditional way to understand a battery in terms of aging and to derive a cost function, as we just discussed, is to really put the battery on a test bench and, well, not one battery, but more like 200 of them, and then test them in every possible scenario. And then what we derive from these tests are curves, as we can see here. This is a very simple test. We just put a battery into an oven at 35 degrees Celsius at different state of charges. Some are charged fully, others are almost empty. And then we just let it sit for 3 years. And what you can see is that the aging rate, or the capacity at the end of the test, changes dramatically depending on the conditions that the battery had. So what we can see here is, not going into detail, but it seems that a lower SOC, a lower state of charge, for this battery will reduce the battery aging significantly. Okay, so if we imagine that for all the different conditions that a battery can have, cycling at which depth of discharge, which average state of charge, which temperature, and so on, we have these curves, then we will be able to say, okay, if you do such and such services in a vehicle-to-grid environment, your aging costs will be this and this. So we have the means to answer this question, but there's one catch. And Aachen University operates about 3,500 battery test benches, and I think the next 1,000 are already on the way in the post. So we are pretty good at battery testing, I would say, and battery tests are by no question the best way to understand batteries. It's the only way to actually really understand batteries. But the problem is battery tests, and everyone who has done one knows it, are complex, it's time consuming, and it's expensive. So if you want to parameterize a lithium-ion battery, for example, this will cost you at least 100,000 euros, and it takes at least 18 months. And to be honest, the significance of accelerated aging tests is to be discussed in the research space. So it's still not clear how these results can be directly transferred to reality, because there's so many side effects going on at high temperatures that it's very hard to give exact prognosis of the aging development. And so if we think about huge research institutions with up to 100 scientists in a research group, well, complexity and time shouldn't be the big issue. But if you think about regular companies, such as the ones we have in this webinar, many of them are just not able to operate battery testing facilities like this. Especially if you think about that, most companies, most system integrators are having 2, 3, 4, some 5 battery suppliers just in terms of supply security. More often than none, battery suppliers just don't deliver anymore for whatever reasons. In the US, currently, Audi is fearing a battery shortage because SK Innovation and LG Chem are suing each other over patents. And so Audi might end up without battery cells due to legal issues. And so they need to really make sure to have a constant supply of batteries. And the way to do it today is to diversify, which means have at least 2 or 3 suppliers. And these suppliers, they're researching, they're developing the batteries, so they come up with new battery generations about every 1.5 years. So this significantly increases the complexity you have on the battery side, and doing lab tests in such a way that we just saw for every single one of these battery generations is very, very hard to do, especially for mid-sized companies. And so we have been looking into ways to come up with a possibility to get at least some of the data that we could do with lab tests in maybe not the same quality, but still something that is very much better than doing nothing by using field data. And it's a research topic that is growing around the world. So many publications on that. Very, very interesting field, because we see the merging of battery science and artificial intelligence. So there's a lot of people, very smart people, streaming into this field right now. And the general idea is most batteries, at least most batteries starting from a certain size, generate data anyhow. So you need to measure current, voltage, and temperature. And by using this data, not of a single battery, but of a few thousand, 10,000, 100,000 battery cells or modules, putting that together and using model-based approaches, using big data, is it possible to come up with answers to the questions that we have, such as what is my cost curve and how can I find the optimal time to switch my battery from a car into a stationary application. And actually, I brought with me some results of what we did. And this is a good example from a stationary application. So we were using only the data that was generated by the system. The sensors were not really exceptional, so very, very standard components. And then we basically applied those algorithms that we have in order to do a virtual lab test with this battery. And then we drove out into the field and actually opened the battery and did a manual capacity test on the site, which of course, the manual capacities on the site is not as good as the one in the lab, but it was pretty okay, I guess. And we can see that the deviation between the results that we have was below a half percentage point in state of health, in amp hours, absolute. And so this is a very reasonable result in order to answer many of the questions that you have in real life, even though it might not be perfect from a research perspective.
All right, Kai Philipp. As promised, here a short cue for you. We have around 5 minutes left.
Great, thank you. I think I have one more slide.
Perfect.
So I think in order to wrap it up, how can research help companies to improve their products and to actually realize the vision that we have of batteries in the energy and mobility space? There's a lot of things you can do in terms of, build better systems because you have better information, improve lifetime and such. And this is actually a real life example from an analysis that we did for a customer on his battery storage systems. These were way more than 10,000 battery systems. I think it's more than 30,000 battery modules. And you can see the average aging rate and the average remaining lifetime of these systems. And you can see huge differences in these suppliers. And this wasn't clear to the company before. And now, knowing that some systems perform significantly better than the other ones, this helps, of course, to make better systems the next time. So the summary, this is the summary actually that I wanted to show. The battery world develops crazy fast, and Zach introduced our talk saying the same thing. It is a very exciting time, sometimes also confusing because you hear a lot of different input from the media and from new revolutions that might not be as revolutionary as they sound in the beginning. I think personally that is crucially important that research and business stay in touch, just in order to bring new innovation into the field. And with that, let's go out and save the world. So thank you very much for your attention. I'm open to questions. If you want to contact me directly, here's 2 email addresses and my LinkedIn, of course. Zach. Moderator, host.
Sorry, I just missed the mute button by a millimeter. Thanks a lot for your keynote, Kai Philipp, and for taking your time to kick off the day this morning. As we go through the Q&A, please also feel free to type your email address and your LinkedIn profile into the chat so people can directly click on it.
Yes.
Awesome. Let's see if there's. I see Tom already has a question for you, so I'll obviously start with the questions in the chat. And to everybody in the chat, please type away your questions. And if we have a little bit of time, I might even invite you later on. to join me via video, although that's something we can do in the sessions, but not here on the stage. So for V2G, as vehicle to grid or second life applications, how does the on-grid power requirement compare the power requirements of electric driving? What does this mean for the aging costs? That's actually, I would have had a similar question, like how compatible is a vehicle battery with a grid application? Yeah.
So generally, for most cars that are in the vehicle to grid in applications, the stationary power demand is much lower. So for most cars, you will just be limited through the inverter of the wall box. So we're talking about maybe 11 kilowatt, maybe 22 kilowatt. So in terms of power, that is not very much for the battery. But we have to look not just onto the battery, but also on the inverter in terms of efficiency. We don't want to burn too much energy by using, let's say, a 50 kilowatt inverter just at 5 kilowatt. So this is another point. But in terms of aging, I would say that the charging power will probably not be the most crucial aspect of it.
Mm-hmm. If we stay with the V2G topic there, and you talked about aging, so I think later on one of the topics we'll have in the sessions is, I think, bidirectional charging as well. So how do you count that into the aging process? Is that an additional cycle or?
So what you need to do really is to have a cost function of the battery, and then you can estimate quite well how an additional cycle, and it won't be, a full cycle. What will probably happen, depending on the application, is you have maybe a 10% state of charge increase, and then maybe a 10% state of charge decrease. So it's a microcycle, and the thing is, depending on where this microcycle takes place, so between 20% state of charge and 30%, or between 90% and 100%, is very, very much different. And our vision is to have an algorithm that knows the cost function and will just independently say, this is economically feasible for me to do because I make more money on the service than I lose on aging, and not have a human have to decide it every single time.
Mm-hmm. Actually, there's so many cool questions coming up, exactly the questions I would ask as well. That's really nice. When do you think will V2G be realistically available in the market? So when will we have, on the one hand, I guess, enough batteries installed in electric vehicles, and then them being out of service and entering the grid market? Do you have a timeline?
I think, well, V2G, so the usage of car batteries while they're still in the car, it will crucially depend on the availability of charging infrastructure and on the amount of cars. So I think that smart charging, so just timing a unidirectional charge, will very, very quickly roll out once we have a need, because there is a very big system benefit in it already. And it's actually pretty easy to, simple, I would say. There's a simple way of optimizing your grid load by giving incentives in terms of, if you charge in 2 hours, you will save a little bit of money. So, and if your car knows, hey, you're not leaving the house before 6 a.m. in the morning, and I just need 2 hours of charging, I can time it whenever is beneficial. I think that will be very quickly. Mm-hmm. In terms of vehicle to grid, so power flow in 2 directions, I would hope it would be quicker, but I think we will need at least another 5 years for that to mm-hmm. play a role.
I actually, in my question, I accidentally mixed in the second life question. That was the one I wanted to go to then, apart from the V2G. When do you think, from what year onwards, will the second life aspect be interesting and relevant?
So I think it's really great that we have many vehicle to grid projects already. Second Life. No, I mixed it up. We have Second Life projects already. So many, well, OEMs as well as energy companies are already very actively looking into this space, which is great. But the thing is, most of them use car batteries that might not have even had a first life. So for some Second Life applications, you just take car batteries that were never used because we don't have enough electric cars that are past a certain age. And so obviously this will change very much in the future, and it will change at different speeds depending on where you live. So if you think about China, for example, that has had a much higher adoption of electric vehicles, for example, electric buses, also in the past, they will certainly hit the numbers that are needed to have a sustainable business earlier. It will take more time in Germany and in Europe. But I think standards are a very important question here, because the transfer costs from a single vehicle to this big facility, they must be close to zero. So we need to come up with really, really smart solutions for that. But once we have the technical standards, I would say car batteries last 7 to 10 years in the car. So I would hope in 5 to 6 years, we'll see the first big installations.
Mm-hmm. We have another question from Günther. Assuming that there are many bidirectional V2G systems participating in grid services, how long would it be until the earning potential is becoming lower than the transaction cost?
Yeah, that's a very interesting question. Demand and supply. So the more people that are active in the market, the less money you can make. And we actually have seen this in the market for frequency control reserve, Primärregelleistung in Germany. 4 years ago, maybe just 3 years ago, you were still able to make about 4,000 euros per megawatt per week on this system service. And since the massive building of energy storage systems for this application, the price dropped down to, I think it's in the range of 1,200, maybe 1,000 euros per megawatt per week now. So the price dropped to 25% of its original value. So I think that a lot of companies learned the hard way that you should not calculate a business model over 10 years with no risk on the earnings side. But I do think, on the other hand, that the beauty of vehicle to grid is that you can provide local services. So local services will probably have different values depending on where you are. But if you are in a highly constrained grid, where you basically would need to switch a transformer or put new cables underground, using your car to stabilize this grid might be cheaper for the grid operator, even in the long term, than to actually put new infrastructure there. But, and this is the huge but, currently they make up to 9% of interest on these new transformers that they built. So they have zero interest in coming up with a cheap solution. And this is difficult because they can pay you to use your car, but they have to pay for it. And if they build infrastructure, they get money for it. This is just the way that the German grid works today. And it would be really cool if we could find a more efficient way to say the least. Yeah.
So I guess that's also a regulation question, or
Absolutely.
a question of incentive.
Yes.
There was a question of Etienne, a little bit higher up already. A big topic raging in Africa is whether there is actual value in terms of life/aging to buy more expensive NMC batteries versus cheaper LFP. What do the facts say?
Well, actually, if I might do a little promotion, we did a very extensive covering of this topic, NMC versus iron phosphate, in PV Magazine. You can still read about it. There were a couple of experts. Some of them I already saw in the list attending this webinar, that were discussing about, hey, which battery is better? Is it always NMC or is it LFP? The answer is you really can't tell. There's no general there's no general statement I can make here. There are extremely well-built LFP cells, there are extremely well-built NMC cells, and there's shit on both ends. So the only way to figure it out is to actually test the batteries, or at least find someone who has used the batteries in a similar application and go talk to them and ask them, hey, what were your results so far? But general statements on chemistry, there's so many other factors that will shift the performance, production quality, and many other things. So sorry, but there's just no clear answer.
Mm-hmm. Maybe as a closing question, since we're already nearing the end of the slot, it's one of the winners of the EES Award 2020. It's a startup. They're actually focusing on a zinc battery. It might still take some time until it's available, but how big, what is your future prediction for alternatives to lithium-ion batteries? Are there some that are, on the one hand, technologically viable, and then on the other hand, also with regards to the economies of scale, will have a chance at all?
Yeah, so I think it's great that we still keep innovating and that we look into new moonshot technologies. You know, this is so important to really stay in this fundamental research space and keep innovating. And you might see where this is going, but in order to beat lithium-ion batteries today, you would need to be at least 2 times better, maybe 3 times better, because just being 20% better doesn't justify switching everything that we already have in infrastructure, in workforce, in knowledge, to something new. And you can see actually how lithium-ion batteries got to the point where they are. How did lithium-ion batteries become so successful? They could run your laptop 2 times longer than the nickel batteries that we had before. And this is something where people were, like, high-end products, were willing to pay money for. They said, I don't care what it costs. 1,000 euros per kilowatt hour, my laptop runs 30 minutes longer. This is awesome. And so they had this very profitable niche, and from there could really disseminate into the market. And if you think about a new technology today with zero scale effects, and lithium-ion batteries are still getting better every year. So it's not that you have to fight against the status quo, but as a new technology, you have to fight against where lithium-ion batteries will be in 5 years. And so honestly, I think it will be very, very difficult. I think in the automotive sector, lithium-ion battery will be there to stay. In the stationary storage system, there might be a place for low energy density, low aging, low cost storage. Redox flow has been talked about a lot, but honestly, I have not seen a feasible redox flow technology that can beat the costs of lithium-ion so far.
All right. Thanks a lot for joining us, Kai Philipp, today. Yes, we've come to the end here. Awesome. Thanks a lot for your presentation.